Everybody okay with that? Of course you are. Question 4. Describe how you would extract the rate constant from a set of data of concentration depends upon time of a particular elementary reaction. Okay, so this is just words, and we've already talked about it. Rate constant of a set of data doesn't tell us what the order of reaction is. So first of all, you need to determine the order of reaction. So you would plot the concentration against time. And if that was a straight line, then you know it's zero order, and then the slope, I'm going out of film screen, then the slope is the rate constant. If it's a curve, then you need to plot the log of the concentration against time. And if that's a straight line, you know it's first order, and the slope is the rate constant. If that's a curve, then you plot 1 over the concentration against time, and if that's a straight line, then you know it's second order. The slope now is the rate constant. And if it's still a curve, either you've made a mistake, or it's not 0 first or second order. And you'll learn how to deal with that next year. Okay, that should be enough for that one. Question 7 then. When I tried to do this, I was doing this last night and I got the wrong answer. I think there might be a mistake in the question, but let's have a look. Okay, ideal gas law. What's the ideal gas law? What are the modifications you need? So the ideal gas law shouldn't be too difficult. PV equals nRT. The question is, what are the modifications? Guys, at the back, why doesn't the ideal gas law work?
Because all gases are ideal.
Why aren't they ideal? What's wrong? Why don't they behave ideally?
They don't behave according to the equations.
Yeah, absolutely, why not? That's what it's asking. It's saying, why don't gases behave according to the equations? What is it? Actually, what it's really saying is, what are the assumptions you make in the ideal gas law?
They're all the same size, and that they don't react.
No, to both of those. But on the right lines.
Is it that 1 mole of gas fills a certain one?
That is the ideal gas law, but these aren't behaving ideally. So what are their properties? What are their properties that the ideal gas law doesn't take into account? Or the other way of saying it is, what are the assumptions of the ideal gas law? Anybody?
Is a rapid haphazard motion?
Okay, that's fine, and that works really well. That's absolutely right. Molecules, random motion, yeah, and it's proportional to the kinetic energy, proportional to temperature. That assumption is sound. Try another one.
Or molecules of the same size?
See, that works really well as well. That's not
No,
quite right.
same speed.
No, you don't assume that. You assume they have a distribution of speeds, and the average of that is proportional to kinetic energy, proportional to temperature. Somebody else on this side? Right, if it was a really ideal gas, and you cooled it right down, what would happen?
Stop completely.
Yeah, it would slow right down, and what else? Yeah, actually nothing would happen. It would stay a gas. Okay, but does that happen? No. So why not? What's the difference between a liquid and a gas? Interactions. So what assumption of the ideal gas law is not obeyed by real gases? I think you all said you assume there are no intermolecular interactions, and you're absolutely right. That assumption is not very good, particularly for things like water interacts like hell, even things like nitrogen interact through the London forces. I don't know if you've got onto those sort of forces. Okay, so that one assumption is not very good, and that's why we use Van der Waals and not the ideal gas equation when we get up to high pressures or low temperatures. It's another assumption we make about ideal gases. Go on.
Is it that all the gases in that system have the same energy or the same velocity?
No, they all have the same. Sorry, there is a distribution of energy, so no, it's not that. Again, let's suppose we compress them right down. What happens with an ideal gas when you compress it as far as you can? goes to 0. That's the ideal gas assumption. In fact, that's how Kelvin got his temperature scale. Was he looked at the volume of gases, the volume of some gases against temperature, and he showed that they decrease linearly, and he predicted that at at minus 273 Celsius, the volume of the gas should go to 0. Is that sensible? Does the volume of the gas go to 0 at minus 273? No, why not? Yes, the atoms have volume, the molecules have volume, and that's the other assumption you make with the ideal gas equation. You assume that the molecules have no volume. They don't. When you put the gas in a box, you assume that none of that space is taken up by the molecules you've just put in there. And clearly that's nonsense, but it works really well until you get to very high pressures, 10, 20 atmospheres, or very low temperatures, minus, take a guess here, minus 50, minus 60 degrees C. Okay, so those are the assumptions that you've made for the ideal gas, and they don't work very well. Sorry, they don't work very well at high pressures and low temperatures. At atmospheric, ambient temperatures and pressures, they work brilliantly. So air behaves pretty ideally. Ammonia's not very good, but air is pretty good. Right, so that's the van der Waals equation, which you need to know. Right, so part B.